Hello, my presentation is on multi-beam lithography. We are going to see the following things regarding this topic. First, we'll see the conditions that led to the development of this technology. Second, we'll see the different approaches that this scheme uses. We can look at the advantages of the multi-beam lithography. Then we can move on to some specific tools developed by startup companies which have demonstrated this successful multi-beam lithography. We can see in specific what the writing strategy of each of these tools is. And then finally, we can move on to the factors affecting the throughput and close off with the roadmap for the future. So multi-beam lithography was actually developed not to replace a single beam but to complement it. When we look at the conditions that led to the multi-beam approach, we can see why it is important in order to maintain the throughput in mask development. Now, as we reduce the node size in the sub 100 nanometer range, 45 nanometer, 30 nanometer, etc., we keep on reducing the node size. So the masks are becoming more complex. In order to maintain the throughput and in effect also keep the costs of the masks in check, we need to go for a parallel electron beam system where we, instead of a single beam, which is far too slow, we have parallel beams working together to etch the pattern. So this in effect offers a high throughput solution. It improves the throughput while maintaining the pattern accuracy and quality. And there is an inherent flexibility in that the current in each beam can be manipulated individually. So we can still maintain the high current at the wafer surface. There are different approaches in multi-beam. 4 of them are listed here, are picturized here. Multiple columns is the most common approach. You have separate columns where the source, the E-beam source gets split, and each beamlet goes through separate columns. And by this we're minimizing the electron-electron interaction. So this is an optimal approach. And there's also an approach where you have a single column and multiple beams are created in that column through multiple sources. In the distributed multiple beam approach, you have again multiple beams but created by multiple sources which are distributed over the wafer, either partially or entirely. And we have finally the proximal probe arrays, where again you have a number of E-beams produced by a dense array of STMs or AFMs. Now, before we look at the tools which employ this multiple column approach, we can briefly look at the advantages. Now, the multi-beam technology came into the picture in the 1990s when people were looking at ways to increase the throughput. Now, because it's been nearly more than 2 decades that the development has been going on, a wide range of electron beam systems are already available. And in turn, we have a wide range of electron beam energies. So that leads us to the most important factor, and that's cost reduction. Because of the flexibility of changing the pixels in real time, it's economical. And even the cost of a column costs several $100,000 versus an optical column, which costs in the millions. So all this leads to a more economical solution. And of course, we can use higher sensitivity resists, which is required for finer patterning. And in comparison to optical systems, the overlay accuracy is better. So coming to tools developed by startup companies, there are three leading companies which I've listed here: Mapper, KLA-Tencor, and Multibeam. And the table at the right shows a comparison of the number of beams and throughput that each system offers. So the technology behind each one is slightly different, although the approach is the same. You have a novel approach called REBL, Reflective Electron Beam Lithography, by KLA-Tencor. And here the electron gun directs the electrons into a digital reflective pattern generator. And that's the main component here. It's a CMOS circuit. You have the mapper, which combines this parallel electron beam writing with a high-speed optical data transport, conventional optical data transport. And then we have CEBL, complementary electron beam lithography, which is which was developed by Multibeam, where you have again multiple columns of electrostatically controlled beams, electron beams, and it's used for critical stages, for example, writing polys and metal lines, vias and holes. And for the other layers, the conventional optical lithography can be used. So moving on to the writing strategies, if we look at Mapper, you have a rectangular slit of a fixed width, and the E-beams are actually confined in this slit. So you have the wafer moved underneath the slit from one end to another, and the deflection is also fixed by 2 micron, and the E-beam deflection goes over this entire wafer. And through this system, Mapper claims that complete fields can be exposed in one scan. So it's supposed to be a very high throughput system. Moving on to KLA10 course REBL system, you have, as I described earlier, you have a digital pattern generator. That's the main component. It's sitting at the top there. So the electron gun shoots these electrons through the lenses, and the lenses will illuminate that generator. And there are a number of metal pads there, and some of them will absorb the electrons and some of them will reflect them through the optics. So it's these reflected patterns, electrons that pattern the wafer. And then finally we go on to multi-beam. Their writing strategy is slightly different. You have again a number of columns of these e-beams. You have a main field deflector which first positions the beam, and then there's a subfield deflector which scans the beam to write patterns. So in this way you can have a selective writing and you can skip over areas that don't have any patterns. So going on to a very important aspect which we have been mentioning all along, which is a throughput. So the main limitations here are to throughput are the electron source. The source should be as bright as possible. The brightness should be very high, and the total current should also fulfill this condition that's stated here. So a second factor is the data path bandwidth. The larger the pixel size, the lesser the time required to write the pattern. So this is again an important aspect that should be considered when designing the system. And the third factor is stage acceleration velocity, which should be matched to the electronic scan length. So coming to the roadmap for the future, currently we have multi-beam systems for photomask writing. They've been demonstrated and they're already, many companies have ordered them. They're in production mode. But the second application, multi-beam for direct write lithography, is still in the early stages. The predictions are that it might take another few years for it to take off, perhaps in 2020. And in 2016, or maybe give or take a few years, 1 or 2 years, we might see the multi-beam approach in the production stage of even 10 and 7 nanometer node masks. So this is how it looks for the multi-beam approach. It's definitely going to complement the single beam approach, and it's a very promising technology which has not which is yet to realize its full potential. So that's my presentation. Thank you all for listening. Here are the references that I used. Thanks once again.